the last lecture, we defined first-order languages, and then we saw how we can use the symbols in the language to form first terms and then formulas. In this lecture, we're going to further look at some properties of terms and formulas. So how can we analyze terms and formulas most efficiently? One thing you probably noticed when you saw the definition of terms is that terms are built inductively, starting from constant and variables. Right? And that allows us to define a complexity notion on a term, which is called the height of a term, which reflects the depth of its definition, going back, how far back do you have to go all to get to the starting building blocks of constants and variables. So formally, the height of a term is defined to be 0 if the term is a constant symbol or a variable, and it's the maximum over all heights of ti's if the term is given as an application of a function symbol to other terms. Of course, for this definition to make sense, we need to make sure that for any term t that is not a variable or a constant symbol, there's exactly one way to write it in this form here. And this property is known as unique readability for terms. Here's a formal statement of unique readability. So let t be a term, then exactly one of the following holds. There exists a variable symbol such that t is equal to v. So in the following, I'll be using this sign here, to be a equality for symbols, right? Just to not confuse it with the equality sign, which is part of the language. So as long as we're dealing mostly with syntactical questions and issues, I will be careful to make this distinction, right? So this just says that as a symbol, right, because as a string, it's equal to this symbol, right? And reserve the use of the usual equality symbol for actual formulas. Now, so the first choice here was that t could be a variable symbol, or it can be a constant symbol, or there exists a number, which is the arity, a function symbol of that arity, and terms corresponding to the arity, terms t1 to tn, such that t is equal to f t1 tn. Moreover, those numbers, the symbol and the terms, in this case here, are uniquely determined. Before we think a little bit about how to prove this, do a little exercise. Show that unique readability for terms implies that the height function for terms h of t is well defined. And looking ahead a little bit, so that one of the major applications of unique readability is that we can prove facts about terms and define notions based on for terms. We can prove this or define it using induction on the term height. Now let's think a little bit about how we would prove unique readability. And as usual, I encourage you to, before looking at the outline here, just think a few minutes yourself how you would set out to prove this. The basic idea is that one first shows that the set of all terms satisfying these three conditions, 1, 2, 3, without the uniqueness requirement, satisfy the closure condition in the definition of terms. So if you recall, the terms were defined using a closure condition in the sense that they were the smallest set satisfying this closure condition. So either you are a variable or constant symbol, or if you are a term, then also and a function symbol, then applying that function symbol to the terms gives you a term again. Right? Since the set of terms is the smallest one satisfying this closure condition, every term must satisfy one of 1, 2, 3. In the second step, then, you use the induction on the length of a term, right, together with this, what you showed in the first step. So you use induction on the length of a term, and that means the length of a term here, not the height, but its length as a string. So just the number of symbols in the sequence as a string, to show that no proper initial segment of a term is a term. And then in the final step, you conclude that the function symbol f, its arity, as well as the terms t1 up to tn are unique. And if that would not be the case, it would have to be that one term would have to be a proper initial segment of another, which would then contradict the second point here. One can define a similar readability property for formulas, again using the fact that formulas are built up inductively from the atomic formulas. So here's the statement. So if phi is a formula, then exactly one of the following holds. It's either an atomic formula, or there exists unique formulas, a unique formula psi such that phi is the negation of psi, or there exist unique formulas psi and rho, such that phi is the conjunction of psi and rho, or there exists a unique formula psi and a unique variable, such that phi is the existential quantification with x over psi. And similar to the height of a term, we can also define the height of a formula using unique readability again. The height of a formula is then assigning height 0 to all atomic formulas. And then if you are in the negation case, you just add 1 to the height of the formula that you negate. Similarly, in the existential quantification case. And if you are in the conjunction case, you just take the maximum of the heights of the formula that you take the end of and add 1 to it. The last syntactical property we have to talk about here is free versus bound variables. So the crucial thing here is that the use of a quantifier binds variables in the sense that they convert them from representing an arbitrary value to being part of a statement that has a truth value. So for example, here x times x equals 2, that's a formula, but x is here thought about to represent any kind of possible and arbitrary value. Of course, if you want to make that statement true, it depends on how you which value you assign to x. Over here, however, right, there exists an x such that x times x is equal to 2. That becomes a statement that is either true or false depending on the domain, on the structure that you interpret this statement over. So something of the nature of a variable definitely changes going from here to here. And that is reflected in the distinction between a free and a bound variable. So essentially here, the variable occurs free. Here, it occurs bound. So to define what a free and a bound occurrence of a variable is, you just do this inductively on the height of a formula. And generally, we just say a variable occurs in a formula if it's just part of the string that defines the formula. And an occurrence that is not free is called bound. And a sentence is just a formula in which no variable occurs freely. So here, for example, we would have a sentence because this x here, as we will see in the formal definition, will occur bound. So here's the formal definition then. So let phi be an L formula and assume we have vk is just a variable symbol. If phi is an atomic formula, then we just say every occurrence of vk in phi is free. Right? That's straightforward because there are no quantifiers in atomic formulas, so there's nothing they could possibly bind. If phi is the negation of another formula, well, there's no new quantifiers introduced here, so the free occurrences of vk and phi are just the free occurrences of vk in psi. Similarly, in the conjunction case, right, there's no quantifier that's newly introduced here, so nothing can be bound here. So we just collect the free occurrences of vk in psi and in rho into the free occurrences of vk and phi. The interesting case is, of course, if some quantification occurs. So in the first case, that's actually the easy one. If we actually quantify over a different variable, let's say VL, right, that's not equal to VK, then the free occurrences of VK, right, because we're only defining the free occurrences of VK in the formula, right, those will not change, right? Those remain the free occurrences, so they are the free occurrences of VK and psi. Only, of course, if we actually quantify over vk, right, then no occurrence of vk and phi is free. So if we really quantify everything inside over a formula, right, so if phi is created from psi using an existential quantifier over our variable that we're interested in, then all occurrences of vk and phi cease to be free. So they become bound.